Okay, folks. So we're going to go ahead now and talk about what's called the central limit theorem, right? And we just wrapped up talking about populations and then taking samples from populations, right? And we talked about different methods in terms of how we go ahead and obtain samples. Now that now that we know what a population is and how we can obtain a sample from them, there's a really important concept known as the central limit theorem, right? So remember, when we have a population, we take a sample from it because we want to go ahead and kind of tell a story about this population, and the sample should be representative of this population, right? So this is actually a really, really pretty awesome mathematical phenomenon right over here that we're going to go through, and it's called the central limit theorem. So let me go over the first bullet point. The central limit theorem states that if you have a population with a mean and standard deviation, and so this, by the way, this icon here that I just highlighted, that's mean, and this icon here is standard deviation. So pay attention to these notations, and take a sufficiently large random sample from the population with replacement, then the distribution of the sample means will approximate a normally distributed, right? So we kind of have a bell curve. That's the normal distribution, right? And I'll show you that in a second. But let's digest this right over here. So you have a population and you take the mean and the standard deviation, right? And now you sample from this population right over here with replacements. What that means is if you keep sampling from this population and you keep getting the means, then when you plot those means, it's going to be normally distributed. Okay, so this will hold true whether the source population is normal or skewed, which means if, for example, in our class, when we go ahead and we take our class, right, we're anticipating, 25 students, or let's just say 30 students or so, that we're going to have somebody who's really, really tall, and then we're going to have somebody who's really, really short, and then everybody for the most part is going to be kind of clustered around the middle, right? That's called a normal distribution. That's this figure that I just skipped ahead to right over here, right? So if this was height in inches, for example, we'd have some that are really tall, and then some folks who are less tall, and then some folks who are really short, and then some folks who are less short. But then for the most part, everybody's going to clump in the middle, and this is going to be the average right here in the center, right? So if this is our whole population, and now we do a random sample, for example, and we keep pulling randomly folks from here, and then we average those, that's going to look like this as well. That's essentially the central limit theorem, right? So, and then so let's talk about this with replacement speeds, right? So let's say hypothetically we take one sample and then we take the average and we plot it on a histogram. We take another sample. This replacement means that everybody then has the same opportunity. They're replaced. They're put back into the population, right? So we have 30 people. We sample 5, right? Those 5 go back into the population the next time we resample, right? So the central limit theorem only works if you're taking the sample multiple times from the same population and everybody goes back into the population, right? That's what with replacement means, right? So again, this will hold true if the source population is normal or skewed, right? That means, again, this is a normal distribution, but let's say hypothetically we go back to our basketball team example, right? If we have student athletes that play basketball, and let's say 5 of the students, for example, or maybe 6 of the students out of the 30 now are basketball players, right? Well, what do we expect them to be? We expect them to be taller. Therefore, this is going to be skewed to the left, right? So this curve would move and then actually peak higher here before it goes down. That's called skewed left. I know it's a little unintuitive. You would think it's skewed right because it's going to the right side, but just remember that it's the opposite. And so even if it's skewed, right, the central limit theorem still applies, okay? So let's go through a example on this one right over here. So the figure, so this is a normal population or a normally distributed population, right? The figure below illustrates a normally distributed characteristic, right? So let's just say we have x here, but let's change x to height because we use that example, right? In the population where the mean is 75 with a standard deviation of 8, right? So this is 75 inches. So this is the average right over here, and one standard deviation is 8 inches away, right? Or 8 inches one way versus 8 inches the other way. Okay, so if we went ahead and took a random sample from this population one time, right? And then we averaged it. And then we plotted that average on another chart. And then we did it again, right? We took another sample. We put everybody back in, and then we redrew everyone out of a hat, and then we did that average again, and then we plotted it again. And we did it again and again. We did it 100 times, 1,000 times, right? After you plot all of that, it's going to look like this, a normal distribution, right? So let's come over. So if we take a random sample worth of replacements of size n equals 10 from the population and compute the mean for each of the samples, the distribution of the sample mean should be approximately normal distribution according to the central limit theorem, right? So ultimately what happens is, so let's come back to this previous slide and let's talk about this one more time, right? So we have 30 students in this group. We randomly pick 5 and then we average it. We put everybody back in. We randomly pick another 5. We put it back in. And we keep doing this, and we do it 100 times or 200 times or 1,000 times, right? After you take all of those averages and you plot it in a histogram, this is a histogram, by the way, right? In a histogram, it's going to look like this. It's going to be normally distributed, right? No matter what. However you do it, that's going to be it. And that's the central limit theorem. So with that being said, I want you all to go ahead and watch this video from the Khan Academy. He really does a better job than I ever would in terms of explaining this. So watch this video. It's about 10 minutes long, and it's going to really give you some great insight on the central limit theorem. And then we're going to head on over to SAS for the next video. Thanks, everyone.